Okay, okay.
I, I, I try to do something with this, it fails. Yes, so it indicates some another my presentation. Let's go. Let's do something in between science and science fiction. So that multidimensional cosmology. The motivation may be different from string theory to some kind of anthropic principle because we know that life and structure of our type can present only when number of space dimension is equal to 3. So that maybe there are some other dimensional world, but there are no witnesses in them. So let us assume that our universe has more than 3 dimensions. And if we assume this, we have two rather opposite requirements. First of all, we know that our 3 dimensional world is to high degree isotropic, so we should keep this isotropy. However, in general, the world should be very anisotropic because we have 3 big dimensions, and other dimensions should be rather small, very small. Apart from brain scenario, of course, because the alternative to compactification is brain scenario when space-time itself is not compactified, but the matter is trapped to some surface. But the problem of brain scenario is that it works well for one codimensions. There are already difficulties in 2 dimensions, and there is a general agreement that it is impossible to do something reasonable in more than two codimensions. So that's why compactification looks much more safe because the number of codimensions may be as big as we want. So that these two requirements are rather opposite. We need to keep isotropy in 3 dimensions, but we have to reach some very anisotropic general configuration. And now I will show you how it's possible to reach these conditions in modified gravity. I mean Einstein-Gauss-Bonnet gravity. So when we add to the action this famous combination of second order curvature invariance, and it is known that in 3 dimensions it is total derivative, so it cannot contribute to equation of motion. But starting from 4 dimensions, it does contribute to equation of motion, and so the gravity is modified. In fact, this is the first non-trivial Lovelock term, so that it leads to the equation of motion, which are still of the second order. If we have general quadratic gravity, for example, if we keep only r square, then we get fourth order equation of motion. If we have this particular combination, we have exactly second derivative equation of motion like in GR. So there are no extra degrees of freedom. And so that, no, first of all, what happens in pure GR when we have only Einstein term, but we allow extra dimensions? Which solution do we have? If we have vacuum, then well-known Kasner solution is still a solution with the same condition for Kasner exponents. So sum of Kasner exponents should be equal to 1, and sum of square of Kasner exponent should be equal to 1. So the same condition, just the sum is not 3-term, but a number of dimensions. If we have Gauss-Bonnet, term, so in principle it's possible to write down similar solution like Kasner solution. So still power law. Scale factors depend on cosmic time by power law. Simply the conditions for Kasner exponents are a bit different. So sum of indexes is not 1 but equal to 3, and instead of sum of squares there is some more complicated condition. However, still power law. But in the case of Gauss-Bonnet gravity, it is possible to get absolutely other type of solution, a solution for which Hubble parameters are constant. So it means that scale factors depend not as power law by time, but exponentially. This is impossible to get in GR. The only such kind of solution is de Sitter solution. the isotropic solution. So if we have meta source on the form of cosmological constant, it is possible in GR to get some kind of this solution, but it is only one solution, this ether. If there is a vacuum, then no other possibility except for Minkowski. However, if Gauss-Bonnet term is added, it is possible to find a solution of this type. So these are equations of motion. It's already written for just this particular ansatz, so I omit all derivative terms. Just after we substitute this condition, then this equation of motions appears to be algebraic, purely algebraic, because all derivatives are set to 0 by this condition. Now I still keep some matter. However, for matter, using this, we immediately understand that there are only two possibilities. In fact, three different possibilities. Either we have vacuum, either we have lambda term, either we have a situation when the overall volume of universe is not changing. It is possible to find such kind of a solution, but this solution is not the topic of my present work, and you will see why, because this condition is really important. So we decide to study a situation where the overall volume is increasing. In this case, the only meta source which is compatible with this ansatz is lambda term, of course. So we will keep lambda term and find solution. Try to find solution when sum of Hubble parameters is not 0, so overall volume is increasing. What is very good is that in this case it's possible to factorize the equation of motion. When the equation of motion are factorized, it leads to very big simplification, because obviously if product is equal to 0, then at least one of multipliers should be equal to 0. Yeah, so when we subtract one dynamical equation from another, because in general we have n dynamical equations, n is number of spatial dimensions. So when we subtract if from this, we get some difference which can be factorized and these three multipliers. And we immediately see that if we decide to study solution when overall volume is constant, then we have no other requirement from here, because it is already enough. So there are many solutions of this type. However, if we decided to study universe with expanding overall volume, then it's necessary to have this product of these two terms is equal to 0. And so that it leads to very severe restriction of possible combination of Hubble parameters. Why? Because suppose we decided to use only first multiplier. Of course, after that we get isotropic solution. Yes, Hg minus Ae is equal to 0 for each combination of G and E. We get that all Hubble parameters are equal, obviously, yes, if we use this. However, if we use only these multipliers set to 0, we get the same, because now we have many equations of the type of sum of this pairwise product of Hubble parameter is equal to some constant value, which does not dependent on the index. So any pairwise product of Hubble parameter is equal to the same value. And this leads to the same conclusion that all Hubble parameters are the same. So that to get something which is not isotropic, it is necessary to use both this and this. We have enough number of equations, because for each pair of indices E and G we have one equation of this type. So we can in some part of this equation choose this, and in other part choose this. However, from here we already seen that it is impossible to get solution of this type with all different H, because anyway we should at least one time use this, and if we use only this, we again get isotropic solution. So there was some restriction on H, and this is just a situation with 4 space dimensions, and it appears that just studying all the possible combination of this condition of first and second condition, what condition is equal to 0 for each equation, it is possible to get only 3 different combinations. Either purely isotropic solution, yes, in any case we can get such kind of solution. If we have cosmological constant as a matter source. Either we have solution with 3 equal h and 4th is equal to some other value, or we have 2 plus 2 splitting of our space-time, h1 is equal to h2 and h3 is equal to h4. No other combinations. So it's impossible to get h1 different from h2, different from h3, different from h4. We have only 3 such kind of cases. When we study 5 plus 1, for example, then we have already 10 pairs instead of 6. And doing the same analysis, which is rather cumbersome, but anyway rather algorithmic, we get only these possibilities. So we get isotropic solution, we get 4 equal Hubble parameters, 5th is equal to something else. We have this interesting combination when h1 is equal to h2, h3 is equal to h4, and they are opposite to each other. And h5 is not fixed, it is something else. And we have 3 plus 2 splitting. Yeah, so instead of having only instead of having 5 spatial dimensions, we, for example, have not get any solution which 3 different h not connected to each other. This is solution for formally 3 different h's, but these 2 pairs should be opposite to each other. So you see that there are big restrictions on h, and it's possible to do this procedure for any number of dimensions. But it is necessary to first to fix number of dimensions. So this is not so algorithmic that we can just input number of dimensions and then go to some procedure. It's necessary to do it for every dimension separately. But we get some kind of possible splittings, which are rather restricted. So first they're published in this paper already 10 years ago, and after that. Vladimir Ivashuk from Moscow, not from Moscow University, from other institute. By the way, he was the first who remarked that exponential solutions, the solution of this time, are possible in Gauss-Bonnet gravity, because usually people are restricted by Kazner solution, because everybody knows about Kazner solution in GR, so usual activity was to find some kind of analogs of Kazner solution in Gauss-Bonnet gravity, but Ivashuk understood that other type of solution is also possible. But his first solution is not interesting for us because it's just constant volume solution. It was constant volume solution. And after that, Ivashuk also contributed very well to this topic, and he proved that the number of different Hubble parameters cannot exceed 3 number of different Hubble parameters, independently of the number of dimensions. So even if we have some kind of 100 extra dimension, anyway, we can get only 3 different Hubble parameters in this type of solution. I do not go to details because it's rather some kind of mathematical manipulation. Nevertheless, it was confirmed just by trying numerically all the solutions. So that we get these solutions. Okay, what is also necessary to think is think about stability of the solution. It's also a result of Vladimir Ivashuk. He proved that these solutions are stable. The necessary condition for this solution to be stable is just expanding overall volume. So that's why constant volume solution is some kind of something marginally stable, so that we are not sure that it can really appear in real cosmological evolution. But as for the solution with growing volume, they are stable except for some exceptional situation, which is also rather formally mathematical. However, we understood that at least one situation is excluded due to this second requirement. This situation is just what? This situation is when we have one-dimensional submanifold. So in this situation, this solution is not stable, so that it cannot appear in real evolution. All other can appear. So, okay, we know that such solution exists, and they also exist in higher order level of gravity if we increase number of partial dimensions, starting from 5 dimension starting from 6th dimension already third Lovelock term, which a combination of some third order invariant of curvature, they starts to be important, and so on, so on. No, at least we checked third Lovelock solution. They lead to the same situation, the same similar solution, exponential type of solution, where scalar field grows or decreases exponentially. That's why I prefer not to call it like anisotropic inflation, because it's not only inflation but deflation also. Some dimension can shrink instead of expand, which is needed for us, of course. So third storm does not destroy this all this situation, except for that now the possible combination will be bigger. So that we know that such kind of solution exists. We know that they are stable in most cases. But the question is whether they really appear in real cosmological evolution. So if we write down the full set of dynamical equation, not putting this ansatz of Hubble parameter is equal to constant, but just solve dynamically, solve numerically, because the system is rather cumbersome. So it can be written rather easily, but in any way it's very hard to find some exact solutions. But it is very easily to run it numerically. And the question is whether we really go to this exponential solution or not. And to understand this, we made just some kind of technical work. So we start with arbitrary initial condition, then put the evolution into computer and to see what happens. And from the beginning, we do not impose any condition of Hubble parameters. So there may be any, but due to one integral of motion which exists in this system, it is impossible to have all Hubble parameters to be positive from the beginning. If we have, if there is vacuum solution, this is possible only if we have lambda term. So usually we start with some anisotropic situation when some dimension expanding, some dimension contracting, and there is no any connections between different Hubble parameters. They may be any. And we start with this, and I just quote the some paragraph from conclusion of this paper, which describes this numerical experiment. So we started from arbitrary anisotropic initial condition and study outcome of corresponding cosmological evolution. The two possible outcomes are regular or singular behavior, because in Gauss-Bonnet gravity, non-standard singularity is very typical, unlike GR, because in dynamical equation in Gauss-Bonnet gravity there are some denominators, and these denominators cross zero, of course all the system blows up. So having finite Hubble parameters, we have infinite Hubble dots, and so the system blows up, curvature invariance blows up, and so this is singularity, which is non-standard singularity according to some kind of heuristical classification. And about half of our trajectory really go to non-standard singularity, and about half of trajectories go to this exponential solution. There are very few trajectories which represent some kind of periodical behavior. This is also cannot be our word. This is not so interesting. However, about half of overall number of trajectories lead to exponential solutions, and there are no other outcomes. So it appears that this solutions which really impose very big restriction on possible combination of Hubble parameters, these solutions are really natural outcomes of cosmological evolution. So we can see some numerical example here, and this is really a fantastic thing, because if anyone would tell me in the beginning of our work that we go to such kind of conclusion, I would say that it is a joke. It's really, we start with anisotropic, totally anisotropic initial conditions. See this, for example, here the 3-dimension expanding, 3-dimension contracting, but all Hubble parameters are different. When time is equal to 0, so it's start of our integration, we have absolutely different number of Hubble parameters, and according to dynamical evolution, with no special requirement, nothing. We just put this on computer and trace what happens. We see that these whole space-times splits to product of two isotropic space-times. This is one more example when we have some kind of zero crossing. So initially we have 3 expanding dimension, 3 contracting dimension, but the outcome we have 4 expanding dimension and 2 contracting dimensions. So in principle, it's not necessary to start from 3 expanding dimension. It can be something like changing in 1 or 2 dimensions, but not more. So as we studied, but we studied only cases with 5 plus 1 and 6 plus 1, so rather low dimensional case. Anyway, a typical situation is that when we have 3 expanding dimensions from the beginning, we end up with some 3-dimensional isotropic world. Sometimes it happens that number of dimensions change. During evolution, one dimension crosses the 0, so starting from contraction goes to expansion, or vice versa. So that what is fantastic thing is that we can get isotropic 3-dimensional space as a natural outcome of totally anisotropic initial condition due to Gauss-Bonnet term. Because in GR we can get only isotropic, so all dimension is isotropized if we have the Sitter solution. It's not our world. Here it's possible. So instead of having lambda term, we have no de Sitter solution. So we can have de Sitter solution, of course, but we can have something else. And this is very good for us because we can split our universe into 3-dimensional world and the inner-dimensional world. It's good. But it is not enough for us. Why? Because in this situation, the extra dimension continue to shrink. And we know that, for example, effective value of Newton constant for our world is just combination of bare Newton constant, which present in Lagrangian, and volume of extra dimension. If volume of extra dimension changing, then the effective Newton constant, which is observed for the observer which lives on this 3-dimensional world, will be changing. It's also not our case because we have very severe restriction of the rate of change of Newton constant. So we need to stabilize these extra dimensions. And it is impossible to do in the flat universe. In flat universe, we get this solution, and that shrinking will be forever. However, situation change when we add spatial curvature. And this is the paper where we considered the whole scenario. So first we split evolution into 2 subspaces using flat equations for flat universe. And after that we say that, okay, the curvature is not important for expanded solution, but curvature start to be important for contracting subspace somehow. But after split appears, it is much easier to write down equation of motion. Now we need not all these 5, 6, 7, however number of different Hubble parameters. We have only 2 different Hubble parameters, 2 different scale factors. And for this situation, it's very easy to write down solution and solve it, especially numerically or analytically study some stability and so on. And so the result is that adding spatial curvature, we can stabilize in the dimensions so that we have some kind of 2-step cosmological evolution, when evolution starts from a rather general anisotropic initial condition, but evolution ends in a state where 3 isotropic big expanding dimension and stabilized isotropic extra dimensions. In principle, we need not the inner subspace to be isotropic, but in our study it appears absolutely naturally. We do not require it, it appears just as a result. So this scenario consists from 2 steps. The first step, anisotropic flat universe evolves to product of 2 isotropic subspaces, and then contracted subspace stabilized due to spatial curvature. What I can, however, add, which is not written here, that our study of stability shows that this scenario works better for negative spatial curvature of inner dimensions, because in this case, if a stabilized solution exists, it is always stable. I cannot explain it by hand why. It's just result of linearizing equation of motion and study eigenvalues, like the standard procedure in dynamical system theory. But for positive spatial curvature. Then it can be unstable, so there are some requirements of parameters of theory. So not for all combination of coupling constant this solution is stable. So in general, negative spatial curvature works better, and this is not so good from some kind of aesthetical point of view, because positively curved in the dimension are automatically compact, but for negatively curved subspace to be compact, it is necessary to have some special compactification, which is possible. Of course, we can compactify flat space to torus, and we can also compactify negatively curved subspace to some compact subspace, but it is some kind of additional procedure which is needed here. And after that, if we ask the question what the observer from the three-dimensional world could observe, then when you substitute the equation of motion that the scale factor of inner dimension is stabilized, so we understand that this observer would observe simple Friedman universe. So there are no traces of extra dimensions and Gauss-Bonnet term. So the only input is that the only consequences of this term is that the constant are renormalized. So instead of bare Newtonian constant, we have some effective Newtonian constant, but nothing else. So for at least on background level. So if we did not study perturbations, maybe in perturbation levels there are some kind of differences, but on background level there is a Friedman equation, Friedman effective equation for three-dimensional world. If the matter source is lambda term or some kind of matter, because matter start to be diluted, so this solution is only asymptotic solution. But anyway, when stabilization occurs, then we return to usual Friedman equations. How much time is to have? Okay, this is what I need, because if matter source is usual matter, then this is the case. So we cannot find the traces of Gauss-Bonnet term and extra dimension studies by studying the background dynamics of universe. But if the matter source is more complicated, there is one situation when it is possible to say that the dynamics is changing qualitatively. And this is an example. This is an example when we choose matter in the form of scalar field, and not only usual scalar field, but scalar field non-minimally coupled with curvature. And since we already know that we have this splitting, so now we just start from already splitted universe in 3 big dimensions and 4 small dimensions. They are negatively curved, so you see the metric here, just hyperbolic sinus. So this is negatively curved subspace. When we have this matter source, it is there are some technical difficulties to get equation of motion for arbitrary number of dimensions. So we need to choose the dimensionality from the beginning, and so we choose it to be 7. And why it is 7, I will say about it a bit later. But after that, we do the same procedure as usual. We add the Gauss-Bonnet term, we get equations of motion, which I decided not to written down all the terms because they are rather cumbersome. But what is really important is this. What is important is the Klein-Gardon equation here. So this is Klein-Gardon equation for scalar field, and this is usual term which you already know, and this is term which comes from non-minimal coupling with curvature. So that remark that there are no contribution from Gauss-Bonnet term here in Klein-Gardon equation. Gauss-Bonnet term contributes to dynamical equations for metric, but not to Klein-Gardon equation because we do not introduce direct coupling between field and Gauss-Bonnet term. And in this case, this is the term which originated just from R, the curvature. And what can we see? We can see what is the asymptotic value of this term when compactification occurs and inner dimension stabilizes. Of course, this is gone, this is gone, this is gone, this is gone. And if we require that h is also rather small, because we need this in our world, even if we have some cosmological constant, this cosmological constant is very small in comparison with natural units, in Planckian units. So this h should be also small, and we even can pose a question whether it's possible to set h in bigger dimensions to rather small number, and the answer is yes, starting from dimensionality 7. That's why I choose 7 as the least number of dimension when we have not only this compactification, but we also can set big h to 0. In 6 dimension, this requires zero value of b, which is unphysical. Starting from 7, it's possible to adjust parameters of the theory so that this resulting h is also equal to 0. So if h is equal to 0, or at least close to 0, this is also gone. What will happen? We have this term, and this term is not vanishing because this is spatial curvature of inner dimensions. And what is the term? When after compactification it is a constant. So we have filed phi. This is constant, yes, coupling constant, non-minimal coupling. This is constant after compactification. So you see that this effective term looks like additional term in a potential. And this additional term is quadratic in potential. If we would like to put it in potential, we need the derivative of this faked potential term should be proportional to phi. The derivative is linear, so this faked potential term is quadratic. And this term can have arbitrary sign because in principle we have not strict requirement of the sign of this coupling constant. So it is possible to choose psi so that this additional term is negative. Of course, the term is in potential, which is quadratic, is just mass term, m squared phi squared. And we need negative, we need that this term is, if this term is negative, then starting from example from lambda phi to the fourth potential, we get famous Mexican head potential. What just we need for Higgs? Because Higgs field requires that potential has some kind of complicated form. The minimum is not in 0. And usual form for Higgs field is just lambda phi to the fourth minus m squared phi squared. Where this minus m squared phi squared term comes from, in usual setting, it is just put by hand in Lagrangian. But in this setting, it's not necessary to put it by hand in Lagrangian. We can start from lambda phi to the fourth, and then just due to non-minimal coupling with extra dimensions, with the curvature of extra dimension, we get efficient minus m squared phi squared term, and as a result, the evolution of field phi ends not in minimum of potential, real potential here, but in the minimum of this effective potential. And this is some kind of results of numerical simulation where we have field phi for quartic potential, so phi to the fourth, and evolution ends some non-zero value, just we need for Higgs field. So of course we see that this is simultaneously with the fixing of extra dimensional size. So that usual self-interacting scalar field behaves as a Higgs field, and so that in this situation the dynamics in multidimensional world is really different from dynamics in the world without extra dimension, because we start with usual potential. We need not to put this Higgs potential by hand. So we generate it. So we start with self-interacting field and get this addition. It's one of possible explanation why we have so kind of complicated Higgs potential. Of course, it is not a improvement of extra dimension because we can put Higgs potential just by hand in our world and not require anything. But if we have extra dimension, there is additional possibility to generate this potential just in some kind of natural way using only dynamical equation of motions. In fact, this is all which I want to say now. Thank you.
Please, is it correct that your approach is not applicable for the case when you consider the usual matter, dust or radiation? Yeah.
If I consider mass or radiation, then, as I told, the effective equation for three-dimensional world is exactly Friedman equation. So after stabilization, before stabilization, we have some complicated system of two equations of motion, one for scale factor in bigger dimension, one for scale factor in the dimension. After stabilization, the equation for bigger dimension is just Friedman, nothing else.
Yeah, but how this dust, this matter appear in your?
I can put by hand matter.
Because from the very beginning you have no dust and no radiation, you have no usual matter.
Yeah, but I need not this matter. If it appears from the beginning, okay, I can write out equation of motion. It appears the effective equation of motion is exact Friedmanian. But if I put instead of dust, matter, or something like that, if I put scalar field with non-minimal coupling, I get this, I get Higgs potential. And after that, I can get the inflation as usual. And so that this is something which is not necessary to modify. After that, I can get some reheating as usual.
Well,
the only thing which is new is that scalar field with self-interacting potential ends up not in minimal, but it gets non-minimal vacuum average.
Okay. Do you have any question?
Alexei, so just one comment or query or question, whatever. See, the Higgs kind of potential, the minimum, you can generate through loop corrections very simply. This is what is done. But now you have done so much extra dimensions that ultimately you can induce Higgs kind of potential with the minimum. Is it the only thing that this scheme gives, or anything else also you can have here?
Maybe there are something else, but it's necessary to study perturbations. At the level of background, then very few corrections to usual Friedman. This is only one which we really detected. If there is, even if there is scalar field but minimally coupled, then there is no qualitative difference. Field just evolves to its minimum and nothing else.
Okay, do you have any question? No?
So in the first part, before putting the scalar field, you only took the FLRW with K negative, etc. to get the dimension contracted, right? In the the generalized Gauss bonnet in the higher dimension. So I am asking that if I take the de Sitter space to begin with, where there is a non-trivial topology, say R cross S3 or something. So how would the compactification topology look like? I mean, is it the spherical compactification or what?
This is an interesting question, which is necessary to study more, because we usually start with a flat universe, because in this case it is rather the simple way to write down equation of motion. But if we decided to study from to start from curved space-time from the beginning, we have so many possibilities in multi-dimensional universe. In 3 dimensions, we already have these 9 Bianchi types, and some of these Bianchi types are in fact the set of types, because Bianchi 7 has some additional parameter. You can imagine what appears in multi-dimensions, and I even don't know whether mathematicians know this classification for arbitrary number of dimensions or not. So there are many possibilities. And that's why we assume that when we start our evolution, curvature is not important, and this begins important only when extra dimensions stabilize. Of course, this is a possible area of study. Just pick up some particular metrics for multi-dimensions, fixing number of dimensions from the beginning, for example 7, pick up some kind of homogeneous but anisotropic curved metric and see what happens. Maybe sometimes we will do it in future when we find some mathematician who explain us how to write down metrics in 7 dimensions.
Okay, thank you very much, Professor, for interesting topic. Next speaker is Davud Katavala from Chennai, India.
Thanks. Yeah. So let me begin by thanking CCSP, Professor Sami, for putting up this meeting. This is the first time I'm visiting the center, uh, and it's unfortunate that I've not been able to visit for all the 3 days of the conference. I'm sure that it was a great event, but I'm looking forward to visiting the center for a longer duration in the future. Okay. The topic that I wanted to speak about is essentially in the spirit, it will be slightly in the pedagogical spirit to begin with, and then I'll describe, but I'll actually describe some of the new technical results, starting from some very basic points which go at the foundations of general relativity. Okay. So that's the reason for the broader title of the talk, non-inertial frames as probes of gravitational fields. And because we are at the Thanu Padmanabhan Center, I just wanted to pay a quick tribute. Sumanto is here, and there is a co-edited volume which has some nice articles covering cosmology, astrophysics, general relativity, everything that Paddy had contributed to. Okay. So very quickly, let me move on to the talk. Plan of the talk is, I will first discuss non-inertial frames, like the title suggests. And we all know, because when we start learning general relativity, those are the frames which get introduced to take us from special to general relativity. Okay. But what I will try to do is I'll try to point out certain subtle physical aspects of these frames of references which are often not highlighted, describe some very recent results which try to streamline what physical nature or physical properties one often has to attribute to frames of references before we make use of them to go from special to general relativity. That is the so-called principle of equivalence. Then I'll apply them to two very simple situations. The first one is the classical twin paradox. That also is something we learn in an introductory GR course. But the other one is not something that elementary, but very popular and very famous result by Unruh, that accelerated probes, if they are quantum mechanical, they will have some kind of a thermal response. Okay, so I'll try to combine all this. Okay, the next part of the talk is to go from single probes. So the idea in the first part is just to analyze non-inertial probes, whether they are classical or quantum mechanical, how they couple to background curvature. The second part is if you take two such probes, and if they are quantum mechanical, what kind of entanglement is, I would not quite use the word generate, but what kind of quantum dynamics, how the quantum dynamics of these set of probes is affected by the background curvature. I have very little to say, although I have included the part on decoherence here. I have very little to say on that, except to point out certain controversies concerning the role of curvature in causing decoherence of quantum mechanical systems. I'll mention it in passing. And if time permits, I will actually also try to describe how all these collected ingredients contribute to a formalism which we have been working on for a few years, along with Paddy and Sumantu, who is also around here, where you try to actually have a different picture of describing space and time, not in terms of standard local second-rank tensor fields, but in terms of something we have called as the quantum metric. And I'll try to motivate how this guy can be constructed from the information that is obtained from what I'll discuss in the previous parts of the talk. Okay. So let me begin. This is just to fix, this is something that I usually show if the audience is broad, than to just fix the domain of work. Since this is focused already on gravity and cosmology, I don't have to actually explain this figure. So let me directly go to the main part of the talk. Like I already said, There are various pieces which I intend to connect in this talk, but I will focus on just this upper left corner, that is the discussion of quantum probes in curved spacetime. Okay. So I'll start with principle of equivalence in its most elementary form, that you can use non-inertial frames in a in flat space-time to mimic certain effects of gravity. And I'll try to question this principle at different levels. Okay. It's an important principle, and non-inertial frames do play a very important role in GR, not just for discussing gravitational effects, but for Mach principle, for understanding the origin of inertia. Then, as I already mentioned, to understand what is called as Unruh effect, which I am going to describe if you're not familiar with it. Okay. So let us try to, and the basic statement, if you have not thought about it, is that anything that you do in an accelerated frame in Minkowski spacetime is a good qualitative descriptor of gravitational effects, and to some extent also quantitatively representing gravitational effects, as long as your curvature length scale is much larger than the length scale associated with acceleration. Okay. So that is the quantitative way of mentioning the principle of equivalence. But the objections to this principle has been raised ever since the inception of GR, but most prominently this was actually phrased in the preface of the book on the book on general relativity by the mathematician J.L. Singh, who asked that, if the non-inertial or accelerated frames are supposed to mimic gravitational fields, and if we also take the second insight of Einstein that gravitational field is represented by Riemann tensor, then the acceleration of this frame of reference must be describable in terms of Riemann tensor of the geometry which it is supposed to mimic. If it doesn't do that, then it is sort of a void principle, okay, because then I don't know in what sense I am representing a given gravitational field. Okay. And just to give a very elementary example of that, we know that Newtonian acceleration of particles near the surface of the Earth is 9.8 meter per second square. And I would ideally like to derive this number using equivalence principle by using curvature produced by the Earth. Okay. It doesn't come out, it's a trivial notion, but it doesn't come out very simply in the sense of curvature produced by the Earth at its center. I'll just try to indicate how to obtain that. And now I'll go to a bit of mathematics. The correct mathematical tools to understand all these things is to understand frames of reference in terms of time-like curves of matter particles. That is the concept which was originally introduced by Einstein himself, in the language of system of rigid rods and clocks. So you place rigid rods and clocks and treat them as physical objects, and then describe how these objects are moving relative to each other and call it as a frame of reference. For you to be able to call it as a frame of reference, you must make sure that the distances between the two clocks is not changing with time. Otherwise, you don't have a concept of what is called as a rigid frame of reference, and that is what we need. Okay. I mean, it's not you can use expanding frames of reference and all those things, but the cleanest way you construct a frame of reference is to just demand that your marker clocks are held at fixed distances from each other. How do you maintain that? You appeal to the equation of deviation that we encounter in differential geometry. So you take any two clocks. Okay, here I am representing clocks by stars which are in some initial position at a t equal to 0 hypersurface. Then they evolve, and I want the distances between these time-like curves to be constant in some mathematically well-defined manner. So I appeal to the equation of geodesic deviation. But first I need to generalize it, because I don't know whether these guys are moving on geodesics or not. And since I'm wanting to describe non-inertial frames, I want to keep the acceleration intact. Okay. So what I'm going to do is start the derivation of deviation equation from the scratch using the Fermi derivative, which is defined in this manner. Okay. This is not quite the usual textbook way of deriving the equation of geodesic deviation, but this is an alternate way. Hawking and Ellis would have a description of this. So what you do is define Fermi derivative of any vector field in this manner, where A is the acceleration of these trajectories, U the four velocities, and R is possible rotation of the tetraeds which these guys are going to carry. Okay. Usually the rotation is set to 0, but you may use not just uniformly accelerating, but even a rotating tetrad. Okay, so I've put that in for generality. And you see that for inertial frames, all these terms are 0, and you just get Fermi derivative as the same as covariant derivative. Okay, so your standard concept of parallel transport and all works well for inertial frames. For non-inertial frames, you can use the Fermi derivative to define relative velocity and relative acceleration. This, I want to emphasize, is the correct generalization of the concept of relative velocity and acceleration when encounters in special relativity. So you just define the first and the second Fermi derivatives of the deviation field, that is the geodesic deviation vector of conventional GR, generalized to non-inertial frames, and you just compute these two guys. And they turn out to have a very, very interesting structure, which is not surprising if you make an analogy with fluid dynamics. The velocity, the relative velocity between any two members of the congruence is given by a matrix which is essentially KAB minus RAB. RAB is just the same rotation matrix which is antisymmetric in A and B once you lower all the indices. KAB is what is called as the second fundamental form associated with this congruence. There is an expression for that in GR. Okay. But a more nicer way of just calling that object is it's the vorticity of the congruence. Its antisymmetric part is the vorticity of the congruence. Its symmetric part is what, for example, in cosmology would correspond to the uniform expansion of the congruence. So if I was working with a background geometry which is FLRW, I would have KAB as 1/3 h, the Hubble parameter, times delta AV, and no antisymmetric part if there is no vorticity. Okay, this is just a generalization of vorticity to generic congruences. Okay, so so the moral of the story is relative velocity between any two congruences is vorticity minus the rotation of the tetrad, and this has nice implication for what is often called as the Mach principle, which I will try to mention if I have time towards the end of the talk. Okay, but for those who are a bit more familiar with fluid mechanics, this equation is not totally unfamiliar. It's often written in 3-vector language as the relative velocity between any two streamlines in a fluid is omega cross z. Both, I'm taking the antisymmetric part of KAB and RAB. It's omega cross x minus omega prime cross x, where omega is the vorticity and omega prime is the local rotation of tetrad carried by each streamline. Okay, if you want to put observers on these curves and you want to say that their relative velocity should be 0, that's the most natural generalization of a rigid frame for me, then you lock the vorticity of the congruence to the rotation of local tetrads. Okay, it's a very interesting condition which is usually used in fluid mechanics as a convenience, but here we are trying to elevate it to a level of a physical principle. Okay, if I want V to be 0, I will lock the vorticity of the I will lock the rotation of individual tetrads to the vorticity of the congruence. I don't have a choice. I need an non-inertial rotating tetrads if I want to have my frame of reference in such a way that individual rods and clogs do not have any relative velocity. Okay. Even more interesting is the second Fermi derivative of this, which is given by this longish expression, but I want you to concentrate just on the middle term here. Once again, from fluid dynamics, this term is very peculiar. It's purely dependent on rotation. Forget about the change of rotation, which is a next order effect, but just this term, if I had no rotation, or if I want the effects of rotation to cancel out from the middle term, the condition I get is omega square equal to twice omega V. Okay, what are these quantities I am talking about? If you write this in a 3-dimensional vector language, this is the vorticity, this is the rotation of individual members of the congruence. If I want the rotation term to be 0, I essentially have a balance between these two terms, and one can show by actually writing this in 3-vector notation that this is representing the balance of centrifugal forces, which is represented by the term quadratic in omega here. This is actually omega cross x, the centrifugal term we encounter in standard classical dynamics. And this second term is twice omega cross v, once I write this expression in terms of the v on top. Okay. So very nice thing. I mean, these are all words, complicated mathematical equations, but I've slightly tried to clean it up in the next slide. My deviation equation has a nice structure. The deviation acceleration has a first term which depends on the curvature. E is just the electric part of Riemann tensor. There's no need to display it here because it's in all textbooks in GR. This is the term I learned in a first course in GR, which produces the tidal forces. Okay. So this is the tidal term. Then the non-inertial effects produce different kind of terms. One is just coming from gradient of acceleration. That is how the acceleration changes from one member to the next member of the congruence. There's a relativistic redshift term. Okay. I call it redshift because, I mean, this is in hindsight, because once I solve for the acceleration profile, this term which survives even in Minkowski spacetime is precisely what produces the redshift, gravitational redshift, or the corresponding version in flat spacetime. I'll demonstrate it as we go along. The next term, like I already said, is omega cross z, that's the centrifugal term. This term I have now written, I have just cleaned up the previous expression, written this part in terms of v. It's a Coriolis term, but Coriolis term coupling not to the velocity, 3 velocity of individual members of the congruence, but the relative velocity, because that's how the v was defined. Okay. And the final term is also something familiar from classical mechanics. It arises whenever the angular velocity of the tetrads change with time. It's usually they are not often displayed. When you write down Newton's equation in non-inertial frame, this term also appears. Okay. So in a very covariant way, the moment you introduce non-inertial frames, you get all the kind of fictitious forces, except that these are not fictitious in the usual sense. Deviation vector is a very physically relevant observable. Okay. So we are not really talking about fictitious forces. These are just terms which seem to have the same structure as the standard fictitious forces. Okay. And now I introduced Einstein's constraint of rigid frames by demanding that the deviation or the distance between any two members of the congruence in simple terms is constant. And this is the equation which has existed throughout the history of general relativity. It was discussed extensively by Pirani and other mathematicians long back. Okay. And there's a mathematical reason for demanding this, which I'm not going into, but you can put the distance z between any two members of the congruence to 0 to characterize a rigid frame. The moment you do that, you get something interesting. You get a differential equation for A. For a moment, just imagine that there was no rotation of the tetrad, so all these terms are 0. Okay. Then you basically get a first order differential equation for A for rigid frames, which has in some approximate sense in which, so if I can treat the Riemann tensor term here as approximately constant, there is an approximate solution. In maximally symmetric spacetimes like d zeta and t d zeta, this will be exactly constant, so I can actually solve it exactly, and this is the solution I get. Okay, that's nice. And in the limit where the curvature term E, the electric part of Riemann tensor, actually vanishes, you do get the very well-known, very familiar Rindler profile. Okay, uniformly accelerated motion in Minkowski spacetime are described by hyperbolas, which are separated from each other in a very special way. That is the Rindler profile you would have done in your first course in relativity. Okay. The frame of reference described by accelerated observers. So this expression must be treated as a generalization of this to curved spacetime. That answers the question I raised in the beginning, that if accelerated or non-inertial frames have to mimic gravitational fields, there must be some relation between the curvature of space-time which it is mimicking, embedded in the acceleration profile of the frame of reference. So this is the information about the curvature. So the moral of this whole story is that if I use this accelerated frame in Minkowski space-time, I would be able to mimic a given gravitational field with a Riemann tensor represented by its electric part, which is En. Not the full representation, because I still don't have information about the magnetic part of Riemann. There are more components of Riemann, but at least the electric part is captured by a uniformly accelerated frame. The magnetic part will come if I introduce rotation. That will bring in, the vorticity will couple to the magnetic part of Riemann. So that information will be embedded in the rotation of the tetrads. That's the part I am not going to discuss, but that is the connection with Mach principle, because if you have rotating frames, what information about the background space-time, local as well as global, can you extract from the local rotation of inertial frames, local rotation of the compass, the so-called compass of inertia. Okay. So that is a prelude, and then you make the model. I'll come back to my elementary statement in the beginning of the talk. How do you get a 9.8 meter per second square acceleration near the Earth's surface from its curvature? So now it's very trivial. You have this formula. You need some model to describe curvature at the center of the Earth. Okay. I mean, the simplest toy model you can have is a constant density solution, the Book-Dahl solution. And then you compute this, you get 9.8 meter per second square directly in terms of Riemann tensor components. Very elementary calculation, but the reason I am emphasizing this is you could not have computed this electric part of Riemann. This is the En which comes in the formula, just by using the exterior Schwarzschild geometry, because there is a discontinuity of electric part of Riemann in the exterior of Earth. If you are just outside the Earth and just inside, these components are different because of the junction conditions of GR. So you have to be very careful that you are choosing the curvature only at the center of the Earth, because it's the center of the Earth that is characterizing the frame of reference for you. Okay. So now that was a very broad discussion about non-inertial frames in curved space-time. I will come back to this. In fact, the way in which we arrived at these set of results was reversed to the way I have described it. Okay. What I'll now describe to you is the relevance of these frames in classical and quantum dynamics of individual probes. Okay. And I'll specifically refer to what is called as Unruh effect, which is that if you have an accelerated probe in Minkowski spacetime, a quantum mechanical probe, then it will behave as if it is thermally excited by a field which is essentially like a black body field with a certain temperature proportional to acceleration. That's the so-called Unruh effect. There are some technical clarifications about the assumptions that go into its derivation, but that is largely the point. Okay. There is also the well-known twin paradox in classical mechanics. So if this was not a quantum probe but a classical clock moving on an accelerated trajectory, then we have things like twin paradox. That is, if there are 2 points on this accelerated trajectories which are connected by a geodesic, I am trying to convert the twin paradox into its mathematical form, just trying to reduce it to its mathematical form. Then the relation between the time as measured along the geodesic compared to the time as measured by the accelerated twin is this, the simplest uniformly accelerated twin. Okay. So that's in the pictorial term, there is a twin which starts from here, moves on a uniformly accelerated trajectory, goes to some other point, and the other twin moves on a geodesic represented by a straight line. The relation between their proper times is basically the content of the twin paradox. Okay. And I hope you are able to see the connection with the first part of the talk. What I want to ask here is how the differential aging of the twin looks like in a curved spacetime. Okay. Why do I want to ask that? Because I want to ask the question whether I can mimic a given gravitational background to an accelerated frame in Minkowski. Okay. In which case I do expect, if I put an accelerated set of twins in a curved background, I expect both the results coming from curvature as well as coming from acceleration itself. How do they mix up? Okay. The calculation is straightforward. I want to describe this trajectory, and I want to describe the geometry in the neighborhood of this trajectory. There are approximations involved, involving derivatives of Riemann and all those things. But the nice things, and I don't want to really go into those approximations. So basically you write down what are called as the Serre-Frenet equations for these trajectories. These are the equations from analytical geometry that describe uniformly accelerated curves in Euclidean as well as Lorentzian geometries. And then you use this form of, this is what is called as the Riemann normal coordinate form of the metric. Often it is only given till first order term in Riemann, but there is a resummation. Okay, there is a nice compact form which captures all Riemann terms, and the only assumption here is derivatives of Riemann are ignored. In fact, there is even a summation known for the derivatives of Riemann, but it's not in a very nice cleaner form. This is slightly cleaner, so I'm displaying it here. And you can use a mathematical package to generate the relation between proper time as measured along. So remember, the problem statement is this. There are these two guys moving on two trajectories. Proper time along this is what I will call as tau accelerated, along this is tau geodesic, and I want to compare them. That's the bottom line. So you get some horrible complicated series expansions, but the nice thing about these expansions, which I have been actually emphasizing for quite some time now, is that there is a certain subset of terms here involving just the electric part of Riemann, which can be summed to a nice compact analytical form. Okay. Now, once we have shown that this function has nice analytic properties in the complex plane, it does represent a series which we are claiming it sums to in a nice manner, and this we have verified as a nice entire function, so it does represent a series. The approximations, the calligraphic RA terms are all Riemann tensor terms which are off the plane of motion. So there is a plane of motion involving 4 velocity and acceleration. All the Riemann component terms of the plane are clubbed into this, but all the Riemann tensor terms which are in the plane, that is the electric component of Riemann, can be exactly resummed. Okay, and that is what I wanted to emphasize. This is the part which you cannot actually obtain just by staring at the series expansion. It is something like writing a series expansion of sin x near x equal to 0. It will not tell you anything about, for example, the periodicity of the sine function, because you are only expanding it around one point, and this is something very similar. The reason I talk about periodicity is because as long as En is less than a square, this expression does have a periodicity in the Euclidean proper time. Okay. Those who have done Euclidean field theory would realize the significance of this, because so far I was discussing, I mean, those two twins could have been two clocks moving on those trajectories. But exactly the same result goes into the derivation of what I mentioned as Unruh effect. Okay. The Unruh effect precisely depends on the periodicity of this relation, the relation between the geodesic time and the accelerated time, when you Euclideanize or Wick rotate the time coordinate. Okay. You can easily see from this expression that there is a periodicity of 2 pi by whatever square root of a square minus en. To the extent that a square minus en is positive, there is a well-defined periodicity. So what we do get is not just a correction to twin paradox, the differential aging of twins, but also the Unruh temperature. There is a calculation which will lead to this result, but final result is that the Unruh temperature detected by a uniformly accelerated probe in a curved space-time, in the limit where some kind of a thermality is obtained, is given by this. Okay. So this is the background calculation leading to it, but in de Sitter and anti-de Sitter, this result has been known for several decades, derived in different ways by Deser and Levin. That is, if you have a maximally symmetric space-time, En is constant, all the extra terms are 0, and you just get this. In spherically symmetric spacetimes, like a black hole spacetime, it produces a correction which does not quite appear in Deser and Levin result. Thanks. Yeah, and you know, I want to emphasize that this correction has been missed in the Deser-Levin paper because of one approximation that is made in the paper. If there is interest, I can address that in the question answer session. For FLRW spacetimes, there is a more exact version of this temperature that can be found, okay, which I have not displayed here, but it can be found. There's something very nice. It's a very recent result. I have not had time to incorporate it here, but there's a very nice partial resummation of even the remaining terms which is possible. Okay, but if you just take the leading result, it will turn out to be this. It's just a deviation acceleration between congruences, the geodesic congruences of FLRW. Okay. So this essentially completes the first part of the talk. I wanted to discuss about entanglement and decoherence. Okay, since I have, I think, roughly 4 minutes remaining now, I will just summarize the results and maybe address some of the points if there is enough curiosity in the question answer session. Okay, but let me just comment on one thing which is interesting. So far I have been talking about linearly accelerated probes in curved space-time. One can do something for rotating probes as well, in which one key result is that for rotating probes, we don't have thermality in Minkowski or in any curved space-time, but for anti-de Sitter spacetimes, we do get some kind of periodicity indicated by the expression before. Okay, all it means is that periodicity is not strictly tied to thermality, which is a result again quite well known in the mathematical physics community. There is something called as a KMS condition, which requires further analyticity properties of two-point function beyond just the periodicity of the Euclidean two-point functions. Okay, so I'll not, I'll just mention this and comment. There are various further generalizations of this result, and most important one that we are looking at currently is Schwinger effect in curved spacetimes. Okay, that's a well-known result for which again I have been recently told that some exact resummations for electromagnetic field are known for the Schwinger effect in flat space-time. Whether one can combine this result with ours, there's a very nice symmetry between this, because the terms summed here correspond to electric part of Riemann. Terms usually summable in Schwinger effect correspond to actual electric field, the electric part of FAB, and how do these two combine? Okay, that's something that is work in progress. I have roughly 2 or 3 minutes remaining. Okay. So I'll just conclude with this. I'll just wind this up and then we can stop. Yeah. So the second part I wanted to talk about, this I will have to skip, but the second part I wanted to talk about, which is recently area of interest for many groups, is the effect of curvature or entanglement and decoherence. How does it connect with the first part? It connects in the sense that I again keep multiple probes, but now I ask if there is any quantum measure that can help me chart out the curvature of classical spacetime using some of the known entanglement measures. Okay, so let me just describe the setup. As you can see, the setup is exactly similar. So I take two probes in curved spacetime, put them on some inertial or non-inertial trajectories, but this time I'm actually interested in the case where these two probes are coupled to some scalar field which exists in the background, scalar or vector or any kind of field, okay, and how the curvature mediates this coupling, or how the curvature affects the entanglement between these two quantum systems that will inevitably arise because it is coupled to a quantum field in the background. Okay. Detectors coupled to a quantum field is a standard quantum mechanical calculation in perturbation theory. Our aim is just to see whether curvature can enhance or degrade. Even that is not the main aim. The main aim is if it does enhance or degrade entanglement in certain limits, can we reverse the logic and use entanglement measures to actually read out all components of Riemann tensor. So this is like constructing a quantum mechanical model of a detector. Classically, it is known that if you have 5 classical detectors, you can actually chart out the space-time curvature. What I'm trying to do is what setup can be done using quantum mechanical detectors. Okay. So in the interest of time, I will just skip these two, all these technical slides, and indicate directly the results that actually give you some information about the entanglement measures. That is, we use log negativity as the measure of entanglement between these two quantum probes, and that has features which essentially are quite sensitive to, I mean, in fact, some of the features here which I have not displayed, oh okay, it is actually displayed, is quite sensitive to the magnetic part of Riemann. This is something which is very, very notoriously difficult to measure otherwise in probes like gravity probe B and something. But possibly, if you have a detector system made out of quantum probes, it can, I mean, of course, I am just computing mathematically a measure of entanglement. There are other measures, and I have to convert it to experiments, but this is the first pass at the topic. So we can read off most of the components of Riemann by using 2 quantum probes instead of a single quantum probe or 2 classical probes. Okay. These are the key takeaways from the talk. I think this is the place I would want to stop, unless there are questions. The next thing I wanted to discuss was decoherence and a different formalism for quantum space-time, which is based on these tools. But I'll skip that part and stop here. We can move on to the questions.
Thank you. Do you have any question for Professor?
Yeah, sir, very excellent talk, because I personally work on torsion and non-metricity based gravity, etc.
Okay.
Yeah, so my question is somewhat mathematical. I mean, it directly doesn't doubt, but a little clear. So could you go back to the first slide where you decoupled the entire
Sure.
Fermi your normal coordinate? Yeah, Fermi Walker. Yeah. So I am asking from a mathematical point of view. I understand the physics. It
Yeah.
is the Lagrange points you are like fluids Lagrange description. So I am asking that,
Yes.
could I think as two tangent bundles, there is a connection, which is the first is the Levi-Civita, as well as the torsion, which is the last term, and the non-metricity, which is
Yes.
given. So is it mathematically making sense? Sorry,
Yes.
mathematically making
Yeah.
sense for the violence? So that's what I am saying. That can I say that it is a mathematical proof that every connection can be decomposed uniquely as a Levi-Civita one, non-metricity one, and the torsion one? So I was just very interested in understanding that. There is a mathematical theorem which says that the connections can be uniquely decomposed, just like you define. The first one is the Levi-Civita one,
Yeah.
and the second one is softly like the non-metricity one, the non-metric one, and the torsion.
Actually, non-metricity has not been assumed explicitly here, but I think I understand. You're talking structurally about the
Yeah,
structure
so
of
the violin among the tangent bundles, so can I say it as a mathematical one?
one can actually incorporate torsion on top of all these equations.
So the last term is not like the torsion, I mean like E
No,
alpha.
that's not quite like the torsion, because here my tetrads are rotating
Yes, so
as
that's-
I decide.
uh-huh.
Actually, what I want to do is lock up the rotation of individual local tetrads
Uh-huh.
to the vorticity of the congruence. If there is torsion on
Yeah.
top, this equation itself will get modified. In fact, I would usually not use Fermi derivative to capture the case of deviation equation with torsion. However, that can be done using the part which let me just complete my addressing of your question, because that's an interesting one. This is the portion I didn't spend any time on, but this is actually solution of deviation equation, which is much more general than the one I showed in the first slide. It's actually the same relation between geodesic time and proper time along the detectors, but the torsion will correct each of the functions that appear here.
I
Okay,
see.
so basically this is the measure of distances between two elements of the congruence that is actually affected by torsion, and the corrections to deviation equation. So here I am talking at the level of solutions. Earlier I was talking at the level of differential equations. So the torsion can be included, but those extra terms are much more subtle than the ones I have displayed, just in terms of rotation of the tetrads.
Because I thought the last term was like the torsion, because
No,
it's
no,
a
no, that
difference
was,
of
yeah,
violence.
I can understand that is,
Yes.
it has the same structure, but
Sure.
for me it was not torsion.
Okay.
Yeah.
Thank you very much, sir.
Have any question? Okay, thank you very much, Professor. Yes, finish this session. Let's go to tea break.